All right, so this is a video that starts out chapter 4. An overview of chapter 4 is that we're going to cover three main topics. We're going to talk about inverses, exponentials, and logarithms. Section 4.1 is only about inverses, but in order to talk about inverses, the very first thing that we need to talk about is one-to-one functions. A one-to-one function is going to be something that's required to be able to have an inverse. So before we talk about inverses, let's deal with what a one-to-one function is. So in a one-to-one function, each x value corresponds to only one y value, and every y value corresponds to only one x value. Now, in our gray box, let me unhide what's here first. Talking about here, different values of the domain correspond to different values of the range. Now, let me discuss with you what this gray box is talking about, this specifically right here. A function is going to be one-to-one if for x values of a and b that are not equal to each other, the corresponding y values also cannot be equal to each other. Now, I want to remind you of an example that we would have talked about earlier in the semester. Think about the parent quadratic or the parent parabola. When we have different x values, so let's talk about 1 and -1, have different x values. The corresponding y values happen to be the same. They're both 1 because 1 squared is 1 and -1 times -1 is also 1. And so in this case, we would say this is not a one-to-one function because even though the x values are different, the y values are the same. So in one-to-one, the big deal is that if your x's are different, your y's have to be different. When you look at example 1 and it says, is this function one-to-one, yes or no? Well, when we look at this first piece here, think about what it looks like. Well, we know that this is a line. And when we think about a line, we have all kinds of x values. If I have two different x values, am I going to have a repeating set of y values? Well, no, I don't. So this is a one-to-one function, simply because the y values are different every time the x values are different. Now, for the second example, the answer, let's see here. See if I can cover that back up. I don't know what this one looks like. It's not a line. I could graph it in my calculator and find out. But if you think about it, can I come up with two different x values that might give me the same y value? So let's just let x equal 1 and -1. And so if you take your 1 and your -1 and you plug it in, both of these are going to become a positive 1. So then you have 49 minus that positive 1. That's going to be 48. So my y is going to be the square root of 48, regardless of whether my x was a 1 or a -1. So in this case, we'll say, hey, this is not one-to-one because even though my x's were different, I came up with a pair of y's that were the same. The easier way to look at this is to think about it with the horizontal line test. A function is going to be one-to-one if every horizontal line intersects the graph at most one time. So you remember the vertical line test for functions? This works the same way. If my horizontal line only touches my graph in exactly one point and no more, then we would say that our graph is one-to-one. Another way to say this is that I have no repeating y values, and I kind of even use that same language up here with this question. So no repeating y values, and it's one-to-one. So if we use the horizontal line test, for these two graphs, we ask ourselves, hey, does this pass the horizontal line test? Well, this is just the cubing parent. It looks like it's been reflected over the x-axis, and so yes, it passes the horizontal line test. However, this is a parabola. No, it does not pass the horizontal line test. It would hit those in two places. So in general, a function that is either completely increasing or completely decreasing over the whole entire domain, it's going to have to be one-to-one. So some examples of this would be our cubing parent or the line y equals negative x. Both of those are either completely increasing or decreasing over the whole domain. Some tests to determine whether a function is one-to-one. We've already talked about the first one, and that is going to be if my x's are the same, then my y's should be the same. If my x's are different, my y's should be different. And this is showing that my function is one-to-one. Test number 2, in a one-to-one function, every y value corresponds to no more than one x value. To show that a function is not one-to-one, find two x values that produce the same y value. You just saw us do this back here in section or example 1, part B. We showed that two different x values yielded the same y value. And so that's what step number 2 says. Step number 3, sketch a graph and use the horizontal line test. And step number 4, just ask yourself, is it increasing or decreasing on the entire domain? If it is, then we have one-to-one. So a graph would help here as well.